Welcome back. Let's get some practice in and finish off the year with a tough practice problem. This is relevant for the civil FE exam and the environmental FE exam. For sure the environmental. For the civil, we have to know basic softening equations, water softening, total hardness, just the fundamentals in case we get conceptual questions. So this one I actually did in the past and completely messed it up conceptually, so I am redoing this to get the concept right. I took for granted the idea of milligram per liter as calcium carbonate. Those units we have to stick with for any water softening question. And also this ties into the concept of why it's important to use the equivalent weights. We'll see that a little bit. Equivalent weights is embedded in milligram per liter as calcium carbonate units. So always for water softening, stick with milligram per liter as calcium carbonate, as we will do. Let's start by slowly reading that problem statement. We're told the chemical analysis of lake water is given in the table below. So we have the ion, the concentration. Concentration is a milligram per liter. Made this tough for a reason. It is a long one. We're going to learn some good concepts. So the concentration is just given as milligram per liter, not milligram per liter as calcium carbonate. Using only the lime soda softening chemical reaction shown, the total lime in milligram per liter as calcium carbonate required is most nearly what? How much lime do we need? So this is the total lime. That's what we want to find. So let's put that on the side as what we want to find. The lime amount basically in units are important, milligram per liter as calcium carbonate for the final units. Now we are given the important stuff in the problem statement. The chemical analysis data is provided for these ions, and we are told only use these. So no, if you're practicing for this FE exam, these formulas are in the handbook. Let me show you. Lime soda softening equations, they are in the handbook. So all of these are basically just shown again here. So using just these, our end goal, find the total lime we need to ensure proper softening. Before we get into the solution, let's talk about these formulas real quick to know concepts. So first of all, carbon dioxide removal. We need to do that. We remove carbon dioxide. That's this part. Remove that. It acts like acidity. And we do remove that by adding what? On the left side of the chemical equation, what do we have here? That's the lime. That's the important lime, which we are asked to find as milligram per liter calcium carbonate. So we add that lime, remove carbon dioxide, and that does raise the pH. The pH will go up, and that raising of the pH allows a proper reaction, which is called the precipitation reaction. We want precipitation to occur. That's why we do this. Raise the pH, remove carbon dioxide. But we do add lime as shown and precipitate out that solid of the calcium carbonate. Now, number 2, calcium carbonate hardness removal. No, carbonate hardness is the temporary hardness that's easier to remove. So in this one, we are removing the calcium associated with that critical bicarbonate ion. And that right there is this. The calcium here is associated with bicarbonate. This is the bicarbonate, or the buffering capacity of that lake or river. That is associated together. That's why it's called carbonate hardness. Calcium, bicarbonate, carbonate hardness together is called calcium carbonate hardness. And we want to remove this by doing what? Again, we add lime. The calcium hydroxide is the lime. Now we go on to number 3. This is calcium non-carbonate hardness. Keyword non-carbonate hardness. This is harder to remove. Non-carbonate hardness is harder to remove. And that's going to be, let's say, the calcium that's associated with the sulfate in this example. Sulfate and sulfate ion, calcium, they're together. Notice it's not bicarbonate. So it is non-carbonate hardness removal. And we do that in this step using the soda ash for this one. So that's going to be the sodium carbonate. And let me denote that right there as the soda ash. So that's important because this question could have asked, what's the total soda ash required? That can be calculated. You can post that in the comments below and let me know what you get at the end of this. Now we continue magnesium carbonate hardness removal. Same concept, carbonate hardness is easier to remove. It takes less money as well. So that part will be the magnesium. And we take the magnesium and it's associated with the bicarbonate, this one, and we remove that using this part, which is the lime. This whole thing, the lime, but this is very tricky. There's a 2 here. We're going to account for that in terms of equivalence. So we do that part for magnesium carbonate hardness. Now we have magnesium non-carbonate hardness. So that magnesium non-carbonate hardness is magnesium. And again, that is associated with sulfate. It could be a chloride ion, but that's non-carbonate. So this is harder to remove. And we use in this one both the lime. This part is the lime. And we also use the sodium carbonate, which is the soda ash. So we also have the soda ash for this one. And lastly, we finish off with the remove destruction of excess alkalinity. Keep in mind this occurs when the alkalinity, which is the bicarbonate, is greater than the total hardness. This is rare, but if this occurs, we have to account for that. And in this one, we actually add lime again. So we add lime and remove that extra bicarbonate, excess alkalinity, too much alkalinity, when the alkalinity is bigger than the total hardness. And the last step is step number 7. That will be the lowering of the pH again after softening. And notice we lower the pH by introducing or adding the carbon dioxide intentionally in that last step. So we add carbon dioxide and that allows us to bring down our pH after softening at the end. So that's the basics behind these formulas. But now let's actually solve this. The lime that we need, milligram per liter, is calcium carbonate for the given data here as shown. So first step, this is critical. Always do this. Always. Use everything in terms of milligram per liter is calcium carbonate. So if the concentration was given already in that, you're good to go. You just use those numbers. In this one, I made it tricky to get practice. Let's convert these to milligram per liter as calcium carbonate for all of them. That's given for this chemical analysis of the lake. Now, going step by step, that equation is not in the handbook for milligram per liter as calcium carbonate, but let's write that. And we did that in previous videos as well. All we do is the following. This is what we want to get. And we take the given milligram per liter concentration, multiply that by 50 on top for the equivalent weight of calcium carbonate. And at the bottom, we take the equivalent weight of the constituent or the species that we're dealing with, which is the same here. These will match. Now, doing that for each one, let's go step by step and do that. So what I'll do is the following. I'll just do a quick table for us. And on here, we have the constituent. And that will be the given ions. And then this is the units of milligram per liter as calcium carbonate. Again, always use these units when doing softening type of calculations, lime amount that we need, or the soda ash. Now we can write all of them down. The carbon dioxide, the very important calcium, this usually dominates. That's the highest one. And then we have the magnesium after that. And the total hardness is these, right? The summation of these is the total hardness, calcium, magnesium. And then we take the bicarbonate ion. That's important when we look at carbonate hardness or non-carbonate hardness. So carbonate hardness is anything, these associated with that bicarbonate ion. And then here we have an important one that's just shown, not so important at the end, but it is a sulfate ion that's given. We could have had also a chloride ion or any negative one. So as given, so we only have this one for this analysis. Now we can continue and just do the calculation, and I'm just going to do the first one, then the rest I'll do in the calculator just to save time. So all we do here is take that value of 22 for the carbon dioxide, and then you multiply this. Always it's 50 on top, and that does come from the FE handbook. That is the equivalent weight of the important calcium Here, calcium carbonate, 50. So it is a 50. The molecular weight is 100.1. When we take the 100.1 divided by 2, we get the equivalent weight. So already, here's something important. We're working with equivalents. I repeat, we're working with equivalents because at the end, we want the same unit of milligram per liter is calcium carbonate, which already incorporates the equivalent weight. We're doing a charge balance. We're not simply taking, let's say, apples and oranges. Like if we take calcium is the apple and the orange is magnesium, you can't just add their molecular weights. You can't just add their masses. We need to use the concept of equivalent weight, which considers the charge. And that is allowing us to, at the end, add everything together. And all of that is embedded in milligram per liter as calcium carbonate. Because let's say that total hardness is adding the milligram per liter of calcium carbonate for the calcium ion and also for the magnesium in milligram per liter as calcium carbonate. Then we can sum both of them up to get one final answer as the total hardness. We cannot do that with the molecular weight. The equivalent weight is what we should always use for softening. Again, think of it, you can't add oranges and apples together when we want to neutralize the charges to get that final amount of fruit. Rather, we have to do something and use the equivalent weight, which is incorporated in milligram per liter as calcium carbonate. Always equivalent weight incorporated in milligram per liter as calcium carbonate. So what we will do here is put a 50 on top for that one. Then we take the equivalent weight of the species, which is the carbon dioxide for this one. So that one we go, the equivalent weight of it is given as 22. So we just use that 22 at the bottom. And for this, these cancel. So that's nice. And we get 50. No, this is 50 milligram per liter as calcium carbonate. Now we do the rest and we just plug this in the calculator. So what we'll do is the calcium for this one, we take the 51 times, we put the 50 on top. And at the bottom for the calcium, it will be the equivalent weight is 20. So let's see, we get that and we get 127.5. That looks good. So let's write that as 127.5. 127.5 milligram per liter as calcium carbonate. Magnesium, you do the same thing. And that magnesium amount is 10. Then take that times, up top is always 50. Then at the bottom, we put the magnesium is in the handbook. So that will be the equivalent weight of 12.2. So put 12.2 at the bottom. Then we do that. We get about 40.9. So let's round this up to 41. So I'll put that as 41. Then you just continue. If you need help with this, let me know in the comments. So what we'll do is just put 132. So that's not bad. For the buffering capacity is going to be the bicarbonate. Equivalent weight is 61. And then the last one is the sulfate. That will be the 106.3. That does also, it's shown here as the sulfate. Equivalent weight is 48. So that's the first step. Always do this if the concentration is not given in milligram per liter as calcium carbonate. Now the next step, this is more of a visual step that I recommend that you do, especially if you're learning this for the first time. We're going to draw the bar graph. The bar graph denoting all these milligram per liter calcium carbonate concentrations as follows. So here, how this works is we start, let's say here at 0. And to the left, it's always going to be the carbon dioxide. So how I'll do that is just put it like this. And that will be an amount in milligram per liter as calcium carbonate as 50. So this will be the carbon dioxide. And the amount to the left is 50. Don't put negative 50. That's always by itself to the left. Then to the right, at the top, we put the positive ions, which are the two dominating ones. Calcium comes first, then magnesium. Then at the bottom, we put the negative anions. That's the bicarbonate and the sulfate. We could have chloride and so on. Keep in mind at the top, we could have other ones. It could be sodium plus, potassium plus. But what's important for the total hardness is a 2+ charge, the multivalent. The multivalent is what contributes to the total hardness. In this case, we only have the dominating 2. Typically, that's what they give. But if you had another multivalent, you add it to the total hardness. That would be a tricky question. So let's start with the calcium. So we start at 0, increase at the top. And I'm going to estimate it something like that. And that will be the calcium 2+. And that amount for that one is 127.5. Then we continue with the magnesium. The magnesium is a smaller amount, so the rectangle shape will be smaller. That magnesium is 41, definitely less than the calcium. And that's typically the case. So the magnesium, I'm going to denote like this. Let me actually increase it a little bit, this amount. And that will be the magnesium 2+ charge. Magnesium 2+. And that will go to a value. No, this is 0, and we're increasing 127.5. So we have to denote this above 127.5. So the magnesium is 41. We simply take 127.5 plus 41 to get this value relative to that 0. So that will be the 168.5 on this bar graph. Now we continue to the bottom. At the bottom, we put the negative ones, negative charge, the bicarbonate, which is the alkalinity. This right here, I'll call it ALK, the buffering capacity of the lake is that, the alkalinity, that's 132. So I'm going to use a similar idea for this and just start at 0, go all the way to, let's say, right here at 132, just as an estimate, and that will be the bicarbonate. So that is HCO3 minus bicarbonate alkalinity. Now we continue with the sulfate. That's going to be 106.3. So I'll just denote that as well. And that will be something that looks like this for the sulfate. And that is SO4, 2- charge. Now I didn't write this, so this is important. This part is 132. And then at the end, we finish off with the sulfate. Take 132 plus 106.3. We get a high number of 238. 238. This should be an 8.3. And that right there is the bar chart. Bar chart. Definitely draw this because now it allows us to visualize what's really going on. Look at this. We can first say that the total hardness is what? Total hardness, it's the sum of the multivalent cations, multivalent, let's say 2+ charge and higher, and that will be just in this case calcium and magnesium. So that total hardness is this, and we can call that TH, and that is 168.5. We just found that right off the bat. So that is the total hardness. Also, we can look at the calcium that's associated with the bicarbonate. When we have calcium with bicarbonate, what do we call that? That's the calcium carbonate hardness. That's this part, calcium with the bicarbonate. So that can be visualized. The calcium associated with the bicarbonate is going to be this part right here, just this. And let me just show it like that. This is the calcium associated with the bicarbonate. So that is simply 127. It goes up to here. These are together, stuck together. Calcium carbonate hardness is that. Now, what's the magnesium carbonate hardness? Magnesium carbonate hardness, go to the magnesium, it would be this part. So it would be that sum to get that value, which is going to be basically this. We take 132 minus 127. Magnesium carbonate hardness. Do we have calcium non-carbonate hardness? We do not. Notice all the calcium is with the bicarbonate. Do we have magnesium non-carbonate hardness? We do. We do have magnesium non-carbonate hardness. It's actually associated with the sulfate ion. So it ends here for the magnesium carbonate hardness, but the magnesium non-carbonate hardness is this part. So that is simply the 168 minus 132 for the magnesium non-carbonate hardness. Hope that makes sense. That's why this is good to visualize. Now, why all of this is important is for a tricky part. we're still trying to get the amount of lime milligram per liter is calcium carbonate, but talking about concepts to make sure this clicks and you have a big picture. What is that? How do we get that? So basically, carbon dioxide removal, this is saying we have the carbon dioxide, we remove that, and there is that lime that we need to consider. It's actually a relationship of 1 to 1. And I did a summary for us here for the factor that we consider, and we're focused on this for the lime. And this one is going to be for the soda ash. All we focus on for this question is this. All we do here is multiply by a factor of 1 for the first one when we remove that carbon dioxide. So that carbon dioxide amount is 50, and all you're going to do simply, it's 50 milligram per liter as calcium carbonate, which is already accounted. The equivalent weight concept is embedded in those units. You just take that 50 times 1 to get the total lime. And you might be asking why. We can prove this. So let's do it real quick for the number 1 and the tricky reaction right here, number 4. Let's see how we get these factors. The same concept applies to the soda ash and definitely that lime factor. So number 1 for the carbon dioxide removal, CO2 removal, looking at that formula, we know we have to deal with equivalents. Again, it comes back to equivalents. So carbon dioxide has 2 equivalent per mole. And the lime, where's the lime? Lime is calcium hydroxide, has 2 equivalent per mole. So if I go the lime factor, this is what we want at the end. So on the top, the amount consumed is the lime itself. So it will be the lime on the top divided by the CO2 removal that we remove in the equation. So the lime is the calcium hydroxide, that is 2 equivalent per mole. And let me write the calcium hydroxide. That's this. And we take this divided by the value for the 2 equivalent per mole. 2 equivalent per mole of the, in this case, carbon dioxide, CO2. So that is, these values are provided in the handbook. Now, how many moles are exchanged in the reaction? So we consider that it's a 1-to-1 molar relationship. That is important for stoichiometry. We're going to actually consider that as well for these equivalent concept, equivalent weight. So we can say here that 1 mole is used. So I'll account for that, cancel the mole units. 1 mole of the calcium hydroxide, which is the lime. And at the bottom, we have the multiply the 1 mole of the carbon dioxide. And notice the moles cancel. Moles cancel. At the end, we get 2 divided by 2. We get 1. So it's saying that 1 at the top amount of lime is going to be consumed per carbon dioxide. And that's why the lime factor is 1. Let's prove this for the tricky one. Number 2, this one. Why is it 2? So if I go in here and go to this one. So notice it's the magnesium bicarbonate. There's a 2 here. So you can just memorize it is a 2, but it's still the same idea. Why is that factor 2? So we take this. This is removing magnesium. So that will be the number 4 magnesium carbonate hardness. I'll abbreviate that magnesium carbonate hardness removal. And that's going to be that reaction number 4. So let me erase this and write this as number 4. Now with that, the lime factor, still lime factor, that is a 2. You can just memorize it is a 2, sticking with those formulas. We use the equivalent weights, so that will be the magnesium bicarbonate, that's 2. And the lime, again, still using lime, which is 2. Calcium hydroxide is the lime. So it is still going to stay as a 2 equivalent per mole for the calcium hydroxide, which is the lime. And that is divided by the 2 equivalent per mole for the magnesium bicarbonate. That is the 1 magnesium bicarbonate. There's a 3 sub 2. And then we multiply this. There is a 1. So actually for this one, it's a 2. Consider those 2 moles. And here 1 mole is consumed. So it's a 2-to-1 molar ratio. So there is a 2 for this one. 2 moles of this calcium hydroxide. and at the bottom it stays as 1 mole of that magnesium carbonate hardness, magnesium bicarbonate. And then we do the calculation, 2 divided by 2 times 2. So that's 1 times 2 gives me a 2 lime factor. That's where all that comes from, using equivalent weights. Now let's get into solving this. Let's finish off strong. Let's do this. So we want, again, the total amount of lime. So we're going to go step by step. What is the lime dose required in milligram per liter as calcium carbonate? And let's see, this is the total amount, and the units will be all in those units, milligram per liter calcium carbonate. We can start with the first one. So that carbon dioxide is consumed. We use lime. Notice carbon dioxide removal using the green stuff, lime. So for that one, you simply put 50. And the factor right there is just 1. So it's 50 times 1. That's all we do. So for that one, the carbon dioxide removal, we take the 50, which is already milligram per liter as calcium carbonate. We accounted for that and did that, this 50 shown here, and that is multiplied by the factor, this factor of 1. So it stays as 50. 50 times 1, and that does give us the 50. All the units here in this column will be milligram per liter as calcium carbonate. Now we keep going. What else uses lime? The key question. Lime required. Calcium carbonate hardness removal. So it's lime used right here when we have calcium associated with bicarbonate. How much is that? And the factor is still 1. The factor will still be 1. So how much of the calcium is associated with bicarbonate? That is going to be this part. That amount, that's simply 127.5. So that one is the calcium carbonate hardness removal. I'll call it calcium carbonate hardness removal. So that will be 127.5, and multiply this by the factor. Again, it will be just 1. That equals to the amount of 127.5 milligram per liter as calcium carbonate. Let's keep going. What else uses lime? Okay, calcium non-carbonate hardness removal. Non-carbonate hardness is harder to remove. Permanent hardness, that uses soda ash. So if this was a soda ash question, you can calculate that. We're going to skip that. It's not relevant to the lime. Let's keep going with lime. Magnesium carbonate hardness removal uses lime, but the factor is 2. You can just memorize that 2 in front. Technically, conceptually, we proved it, why it is a factor of 2. So that's magnesium carbonate hardness. How much do we have of that? How much magnesium carbonate hardness do we have based on the bar chart? Magnesium carbonate hardness is this part associated with the bicarbonate. So that is 132 minus 127. 132 minus 127.5 is 4.5. So that is the magnesium carbonate hardness. I'll call it magnesium carbonate hardness is 4.5. Are you just going to keep 4.5? Be careful. Multiply that by 2. So it doubles and we get the 4.5, actually 4.5 times 2 will be 9 milligram per liter as calcium carbonate. We're almost done. Hang in there with me. We are done with 4. This also uses lime. This is magnesium non-carbonate hardness. It does use lime. Also soda ash. We're focused on the lime. So the magnesium that's not associated with carbonate hardness is going to be how much? That is this part right here, and that is specifically 168.5 minus 132. So we take 168.5 minus 132 and we get the 36.5. So this is magnesium non-carbonate hardness removal. Magnesium non-carbonate hardness, and that will be the 36.5, and we multiply this again. The factor for this one will be 1. So that will be magnesium non-carbonate hardness. Multiply that by 1, stick to 1, and that brings us 36.5 milligram per liter as calcium carbonate. And the last thing is saying lime is used when we destroy excess alkalinity. Do we have excess alkalinity? Excess of the total hardness. Do we in this case? We do not. Notice the alkalinity is this part. Alkalinity is 132, this value. So the total hardness is 168.5. alkalinity is below. We do not have any excess alkalinity. So here, this step, we just use 0 lime. We do not use that. And this last step, number 4, does not use any lime. It's not in the equation. So to finish this off, all we do is go in and take the summation of all of these. This will equal to the total lime that we need in milligram per liter as calcium carbonate 50 plus 127.5 plus 9 plus 36.5. We get exactly something very close to 223 units or milligram per liter as calcium carbonate for the answer. And that right there is how we do this. You can again do the same steps for the soda ash that we need. Hope you found this helpful. Hit the subscribe and like button below and keep up the good work.